All right, we've got a lot to cover and not a lot of time, so I'm going to jump right in here. All right, it's 2022. Today we carry advanced computers around with us wherever we go. 30 years ago, this sort of power and portability existed only in ideas and dreams. It wasn't until 50 years ago we could even own a personal computer. And 80 years ago, modern computing itself was just being realized for the first time. Our story today begins roughly 100 years ago. I am Ryan Jones, and today I'm going to tell you the tale of Schrödinger's cats. Act 1, the cat. Our story begins with a thought experiment. A cat, a flask of poison, and a radioactive source are placed in a sealed box. When radioactivity is detected, the flask is shattered, releasing the poison and killing the cat. Erwin Schrödinger proposed this at a time of great change in the world of physics. You see, at the turn of the century, we thought our understanding was complete with Newtonian physics, and then along came quantum mechanics. Erwin Schrödinger, there we go. Okay, now keep in mind, Erwin Schrödinger is a Nobel Prize winning physicist. I am not, so consider yourself forewarned. Schrödinger designed his thought experiment as a means of visualizing the Copenhagen interpretation of quantum mechanics. What this means is quantum mechanics is complex, open for debate, and commonly misconceived. You see, there is no definitive historical statement of what the Copenhagen interpretation actually is. In fact, the term itself was coined by Werner Heisenberg, who meant it to signify the correct interpretation of quantum mechanics as compared to the more nonsensical interpretations as he saw them. According to quantum theory, it is impossible to predict when a particular atom will decay, regardless of how long the atom has existed. In his thought experiment, Schrödinger places the radioactive particle in a sealed box, along with a cat, some poison, and a means of releasing the poison when the radioactive particle decays. Recall that it is impossible to predict when that decay will occur. According to the Copenhagen interpretation, until we look at this particle, it physically exists in both states, decayed and not decayed. Thus, the flask is broken and unbroken, and the cat alive and dead. Until we unseal the box and look inside, the entire system exists in a state of superposition. A superposition can be defined as the ability of a quantum system to be in multiple states at the same time until it is measured. Of course, the cat cannot truly be in superposition as the physical laws of the quantum scale do not apply at the macro scale, but this is purely a thought experiment. Perhaps our thoughts should instead be in asking Mr. Schrödinger, why are you trying to kill our beloved pets? We'll come back to him in a little bit. Now I want you to envision a different box. This one is also metal, but with perforations designed for airflow. It is slim and deep, and inside are billions of transistors meticulously arranged. This box is, of course, a computer, or more precisely, a server, which is but a computer, albeit much more expensive and reliable. Like a race car designed for the 24 hours of Le Mans, a server is a purpose-built machine designed to run at peak performance for extended periods. Unlike conventional races, which compete for the best overall time, the 24 hours of Le Mans is won by the car that covers the greatest distance in 24 hours. With the 24 hours of Le Mans, racing teams must balance the demands of speed with the car's ability to run continuously without mechanical failure. A cheetah running full tilt is the fastest land animal on Earth, but even she will need to pause for rest or risk running herself to death. A server, on the other hand, is the race car designed not only to run at full speed, but to do so continuously for days, weeks, and months on end. But why call it a server? A server is called a server because it serves. It provides services and functionality to other computers. These computers which use servers are called clients, and this model of sharing is called the client-server model. Servers are, of course, the backbone for nearly every aspect of our digital lives, from this call to our email, to our video streaming and shopping. Every request, every email, every ad, every bit of data that is served up and is processed by a server. Classic examples of servers include file servers, database servers, mail servers, DNS servers, web servers, media servers, and this list can go on and on. Now, every first server needs a home, a place to power up and serve. For many, this home often began in the form of the server closet. Perhaps you've worked at a startup or a computer lab with a server closet. Maybe these haphazard messes of computer equipment and cabling is all too familiar. Did your closet have dedicated cooling or just a fan? How about a battery backup? What sort of fiber line was running into the building? And who had access? Perhaps your shop or lab was organized and purchased a rack and color-coded their cables into neat flowing bundles. And perhaps you even had an interactive terminal for administering each server. Sorry, there we go. Speaking of, you now had dedicated servers for each function. For example, you had a mail server, a dedicated file server, a web server, and maybe even two, and dedicated database servers. And each was upgraded and patched individually with extreme care and extreme caution. To deploy an application, you would simply copy your packages and files, update a bit of configuration, and voila, deployment complete. If you needed to troubleshoot anything, you remote onto each host and rely on such tools as grep, sed, and awk. But as time went on and we acquired more servers, we outgrew our server closets. Further, we needed reliable access to power, internet, cooling, and security. So where did we go next? Act 2, the cattle. As business grew and demand necessitated, companies began moving their servers to data centers. Data centers provided the infrastructure required for high bandwidth business at scale. And that's the key. Data centers provided this reliability at scale. Some of the major selling points for data centers included fiber. You want lots of data paths. The more, the better. Power. Data centers provide redundant and reliable power. Heat removal is strategically planned and optimized. And what sorts of data are you storing? Who should have access? Data centers consume a lot of energy. Renewable resources are a way of bringing down their long-term costs. Now, data centers have different capacities, but many larger multi-tenant or cloud-based facilities host over 100,000 servers each. With roughly 2,000 data centers, the US is home to nearly 1/3 of all worldwide data centers. About 10 years ago at CERN, Gavin McCants gave a presentation entitled Data Center Evolution. In there, on one slide in particular, he helped spark a debate and conversation about how we treat and talk about our hosts and infrastructure. With a single slide here, he had introduced the world to the metaphor of pets versus cattle. Now, actually, it just so happens this idea for a metaphor may have originated prior from somebody else. Randy Bias may be the source of this meme from a presentation he gave a bit earlier that year, and that may have been derived from a concept in Bill Baker's presentation on scaling out SQL Server. Regardless, let's discuss these two models. In the pet model, each host is given a loving name. Each is unique with a specific number of cores, RAM, storage, and OS configuration. Each host is lovingly cared for, being hand-patched and upgraded with the utmost care and caution. And when a host malfunctions, we troubleshoot and repair it. In contrast, we have the cattle model. In this model, hosts are not given names so much as they're given numbers. Hosts are roughly identical with only a bit of difference in name and IP. We use automation tooling to manage these hosts. And if a host fails, it is replaced. And more importantly, is that this sort of event is a non-event. In other words, there is no disruption to service. In contrast to the pet model, the cattle model, when we need more hosts, we add more. We grow the herd. And by adding more, what we're talking about is scale out. So let's take a moment and discuss the concept of scale up versus scale out. Recall that pets versus cattle may have been derived from a presentation on scaling out SQL Server. So scaling up, or vertical scaling, is increasing capacity by adding more RAM, CPU, or disk to a single resource. Whereas scaling out, or horizontal scaling, is increasing capacity by adding more hosts. In place of running a single instance application on a larger, beefier host, you instead add more hosts and spread out the workload. You can imagine scaling up has a theoretical limit as well as an exponential cost. Scaling out is theoretically limitless, and the cost associated is relatively linear. Now, the cattle model does not restrict you to a single class of servers, simply that servers of a given class are similar. For example, you may have a compute class and a storage class, each with its own set of requirements. The cattle model proliferated with the rise of virtualization. Suddenly we could carve up a large server into many smaller hosts, and these can be managed, upgraded, and patched en masse. Virtualization provided numerous benefits over bare metal deployments. First, you had increased efficiency. Servers that were once underutilized could now be configured to be effective and efficient. This obviously leads to a reduction in cost. With better or more efficient use of resources, you can do more with less. Increased resiliency. Physical servers require part replacements that could take hours or days, whereas virtual machines can be cloned or replicated in a matter of minutes. Increased agility, teams can provision new hosts or even new environments on demand and even tear them down. And lastly, there's an obvious reduction in waste in hardware resources, energy consumption, and rack space. To build and manage this new virtual infrastructure, we relied on such tools as VMware, Chef, and Puppet. And VMware, we carved up our physical hosts into smaller virtual nodes, while Chef and Puppet automated configuration management. The virtualization revolution was perfectly well with another revolution just starting. We started breaking up our monolithic applications into microservices. Now, first, what do we mean by monolithic? By this, we mean the application is one large self-contained system. It houses all functionality required, from user interface to data access. It is an application designed without modularity and often without fault tolerance as well. A microservice, in contrast, is a small, fine-grained service that communicates over lightweight protocols. They lend themselves well to scaling up or down as needed, and fault tolerance is built in by design. Microservices can be defined as an application composed of loosely coupled services. This does not make an application simpler, quite the opposite, in fact. So why add complexity into our systems? Well, the simple answer is the benefits outweigh the costs. As mentioned, our monolithic applications were not modular. Every change, no matter how small, required a full build and regression, a full deployment. And because this was time consuming, deployments were often bundled with months worth of changes, making deployments stressful and error prone. This was typically managed via two prevailing development processes, waterfall and agile. With waterfall, our applications went through lengthy cycles of ideation and design, coding and QA, and stressful, infrequent deployments. I am, kiddo. Yeah, Mom, you need to go by mama. Sorry about that, everyone. With waterfall, our applications went through, okay, there we go. Agile improved on this by time boxing these cycles into smaller loops. With new tooling available, teams were able to deploy more frequently and even begin taking such concepts as CI/CD to the extreme. Microservices could be developed and deployed independently. Often the smallest changes could be reviewed, tested, and deployed the same day. Microservices could reduce development risks and speed up delivery times. Of course, there was another migration occurring at the same time as well. AWS had been the dominant cloud provider, but they were now joined by competition, first from Google Cloud, then with Microsoft Azure. And yes, there were other players in the field as well. Many companies and organizations were now lifting and shifting their entire operations to the cloud. Further, AWS was now offering something rather novel, Lambda. First introduced in November of 2014, this was a computing service that ran your event-based code and automatically managed the computing resources required. This was our first major introduction to serverless computing. Serverless? Wow, we are a long way from the server closet. Act 3, superposition. We're running our dozens, hundreds, or even thousands of microservices inside VMs, in data centers, and the cloud. How do we keep track of everything? How are we monitoring all of our servers, VMs, and microservices? How do we know when something fails? We need tooling that enables and empowers our high velocity teams. We need a cultural shift, a mindset, a set of philosophies. We need DevOps. DevOps is, of course, a combination of development and operations, and it is the culture of philosophies, practice, and tooling designed to increase the speed of delivery of our applications and services. DevOps enables us to deploy faster and more reliably. Now, this is not a new or groundbreaking philosophy. It is simply a codification of all the best practices tried and tested and iterated over many years of software development, delivery, and operations. When we had our pet servers, we could monitor each host and application individually. We had dashboards, even monitors, dedicated to the display of our server stats and key metrics of our applications. As we virtualized and migrated to microservices, our dashboards evolved. Dashboards started looking like Christmas trees of green dots and occasional red or yellow twinkling lights. We were operating and monitoring at scale. To achieve a sufficient level of monitoring, we employed a series of techniques. Push. This is an agent-based pattern where we install a piece of software, the agent, on our host, and it'll push the events and metrics to some destination. Examples of push-based monitoring include the New Relic agent and the Nagios agent. Pull. In this pattern, there is no agent. A collector service will reach out intermittently and gather stats and metrics. Examples of pull-based monitoring include Nagios agentless collection, and of course, nowadays, Prometheus. Ping. Now, this could be either push or pull. In a pull implementation, there's a service that intermittently checks a series of IPs and ports or endpoints to determine a healthy or unhealthy state for each. Many products provide this sort of functionality, including Nagios, Zabbix, New Relic, Elastic, and more. In a push implementation, services are expected to continuously signal their health by making a request to a monitoring service or posting a message or some other means of signaling healthy, like a heartbeat. And if a beat is missed or stops, then maybe we've entered an unhealthy state. With agent-based monitoring, there are several considerations and concerns. First, you're installing a piece of software from a third party behind your firewall and onto your servers. Is this third party trustworthy and reliable? How about including all of their dependencies? Remember Log4j? Second, can you install the agent everywhere it is needed? Are there hardware or software constraints? And third, how much overhead is added? How much RAM and CPU does the agent consume? If we're scaling this out to hundreds or thousands of VMs, that last consideration could compound quickly. Agentless monitoring improves on this by removing the need for installing third-party software on your private host. For a ping example, we have an Elastic Heartbeat dashboard here. This would be similar in New Relic, Nagios, or Zabbix. For each endpoint being monitored, you can see the history of health checks, including any successes or failures. And when an endpoint fails repeatedly, you can configure an alert and a means of notification. Push, pull, and ping. At a basic level, this was our monitoring. Yet more changes were coming. A new ship pulled into the port, filled with many lovely, lovely containers. Containers were yet another virtualization technology that sped up application development by isolating everything needed to build and deploy applications, including code, dependencies, configuration files, and system libraries, yet all without the need and overhead of an operating system. And container technology had been around for a long time, but in 2013, it was Docker's developer-friendly container format that pushed the technology past its tipping point. And cloud providers were quick to support containers as well. At the November 2014 Developer Conference, Amazon announced ECS, Elastic Container Service. Then in 2015, after having been donated by Google to the Cloud Native Computing Foundation as a seed technology, Kubernetes v1.0 was officially released to the public. And with that was also released to their cloud platform with GKE, Google's Kubernetes engine. Finally, at reInvent in the fall of 2017, Amazon announced plans for EKS, Elastic Kubernetes Service, and they weren't alone. Kubernetes was coming to every major cloud provider. Now let's take a moment to discuss virtual machines as compared to containers. Containers and virtual machines are very similar resource virtualization technologies. Virtualization is obviously the process in which a single system resource like RAM, CPU, disk, or networking can be virtualized and represented as multiple resources. Whereas virtual machines virtualize an entire machine down to the hardware layer, containers only virtualize the software layers above the operating system. As a result, containers consume less resources and spin up in less time. Simply put, containers are smaller and faster. With all of this increased speed and agility, however, came greater complexity. And in order to really take advantage of containers and reap the real benefits, our applications and services required further re-architecting. Now, if you already started breaking down the monolith, then containers were an ideal solution to the problem you didn't even know you had until you did. As it is with the law of unintended consequences, here solving one problem simply leads to the next. Our once primitive, single instance, gigantic monoliths running on bare metal servers are now distributed across multitudes of tiny services, running in containers, scaled for high availability, running everywhere. And so we rely on Docker, Kubernetes, and the cloud to simplify the immense complexity. We build, ship, and run our services anywhere. If an instance or service fails or dies, a new instance is automatically spun up to replace it. Our applications are now more highly available than ever before. But how do we know if we need more replicas? How do we know if a container has died and a new one replaced it? How do we monitor a system of continuous change and adaptation? I mean, this isn't quantum mechanics, but right. Let's revisit Schrödinger's thought experiment. We couldn't determine the state of the system without unsealing the box. The radioactive source was decayed and not decayed. The flask was broken and unbroken, and the cat both dead and alive. The whole encapsulated system was in a state of superposition. Recall that superposition is the ability of a quantum system to be in multiple states at the same time until it is measured. If we look back on this, the trigger mechanism to break the flask is based on detecting radioactivity from the decaying radioactive source, right? So by detecting, doesn't that constitute measurement? We're extracting information. The wave function collapses and reduces to a single eigenstate. The act of detecting radioactivity is the measurement. Well, it just so happens Docker and Kubernetes provide a similar sort of monitoring for our containers. When a container becomes unhealthy, it is killed and destroyed. But that's not all. A new container is spun up to replace it. Our services and applications run inside sealed containers, and container orchestration is maintaining the desired, healthy, alive state. At any given moment, a service could have an instance die and instances still alive. The container orchestrator's job is to actively monitor container status and not only control routing to the healthy containers, but killing and destroying unhealthy containers while also spinning up new instances to maintain this desired state. Now, every time we think we have it all figured out, that's when we're prime targets for disruption. I want to leave you here with a thought experiment of our own. We've broken down our monolithic applications into smaller and smaller services. We've carved up our physical hardware into the smallest of virtual boxes. Our systems ensure that our services are alive, healthy, and highly available. The whole system, while in a constant state of change, exists in a perpetual balance. A node may go down, bringing with it all containers that were running on it. No one panics, our containers respond, and our services live on. At any moment, there is a probability that an instance of a service will die and some requests may be impacted. But without measurement inside this sealed system, can we determine if our application is alive, dead, or both? Is our application in a state of superposition? Of course, this is not how it ends. We don't rely on probability to determine the fate of our containers. We can measure within our systems, and we test and monitor the entirety of the system. We don't play dice with our applications. We adapt our tooling, dashboards, and alerting to fulfill our evolving needs. It is still the same host levels being carved up. Memory, CPU, disk, and I/O. A century ago, the world of physics was disrupted by quantum mechanics, and for decades, computers have disrupted traditional industries. While our applications today are not in superposition, in quantum computing, qubits actually are. Now, who knows what the next 100 years may bring? Once again, I am Ryan Jones, and thank you for your time.
Thanks, Ryan. Great presentation. I know a lot of people are wondering right now. So I know they're wondering because we have a ton of questions. Oh, sorry, a ton of questions for you. So let's get into that one. So the first one, everybody, this one got a lot of questions on this. Do you have any pets or cattle?
We actually don't have any pets now. I've had pets, but now I have 4 kids. So that's my cattle.
There you go. You heard them all together, you know?
Yes.
Okay. So on to some more questions that apply a little bit more. Can all apps be containerized, or are there certain architectures that work better?
That's a very good question. I really like this question because we've had a lot of services, applications go, from bare metal to containerization, and there's certainly better advantages to re-architecting and making it container friendly. A lot of the Java applications that were Java 8 and prior, they didn't have good resource management, and so you saw a lot of when they moved to containers, you saw a lot of resource consumption. I mean, 4 gigabytes of memory was probably a minimum for some of the services, which is not ideal for containers. You don't want to be so resource hungry with your containers. So yeah, moving to re-architecting it to be more container friendly is now one is upgrading Java. 2, you could go to Go or Node or different languages that for your base images that are possibly going to consume less resources.
Okay. Which is kind of a good transition into this next question is, how do requirements on latency impact your decision-making process around scaling vertically or horizontally?
Yeah, that's a very good question as well. I think a lot of that has been, you have trade-offs. You're going to have latency versus your higher availability. I think in a lot of the talks that we've had yesterday and today, it just shows that, you're going to want to choose the higher availability. Your impact of if you're depending on one database server, for example, that's often a constraint, or in the past it's been like one of the constraints. You're relying on a single instance for failure, right? If there's any possibility of spreading that out so that you don't have that possibility of extended outage for any number of reasons. It could be maintenance, it could be an accidental node going down, or it could be a network switch going down. Right? There's so many possibilities of failure. Which again this morning, great talk from Gunnar. There's so many possibilities for failure that you want to minimize that, and the way to minimize that is to spread it out. And the trade-off there is, you might not have. In the example of the database, maybe it's sharded out. Maybe there's some data on different hosts, or however it works. You might have trade-offs in your performance, but you're going to gain that in the higher availability and reliability.
Mm-hmm. All right, thank you. How does the cattle model work on premise when you have fixed infrastructure?
So we are actually still on-prem, and we're using Docker Swarm. We're in the process of migrating to Kubernetes, but it's a similar, whether you're in the cloud or on-prem, you can still have the cattle model. For us, it was we started treating it as the cattle model just by moving to the container orchestration. But virtual machines as well. VMware was one of the front runners years ago, and that's really when we started shifting toward the cattle model. You stopped having that one server that you really depended on. You remoted onto that server, or a number of servers that you may have remoted onto, and now it's instead you had 10 or dozens, or in number of servers that you are now deploying to, and had at your whim. And of course, again, these are going to be virtual. They're either virtual machines, or in the case of containerization, they're now nodes in this container orchestration managed cluster.
All right, awesome, thanks. All right, looks like this is going to be our last question. So we've seen situations where cattle servers have issues and replaced. There is no way to troubleshoot the servers that have been replaced. How do we get around that?
So this is sort of dependent on whether or not your cattle servers are physical or VMs. In the case of being VMs, if your cattle servers are VMs, you're not going to try to troubleshoot necessarily. Maybe there's a reason to troubleshoot, but more often than not, you're going to replace it. You're going to spin up a new instance off that base image. There's any number of reasons where that instance could have gone into a bad state, and perhaps it was on a node that actually went into the VMs are obviously running on physical nodes. That physical node may have gone down from some reason. It could have ran out of resources, right? Again, Gunnar's chaos engineering, right? You want to test the stuff out. So that, if it's a physical node, obviously that you might actually repair that, and you might bring it back in. You can still have physical nodes being your cattle. But really it's going to be your virtual nodes, and you're more often kind of just replace it.
All right, thanks for unpacking that, Ryan.